In this video, we are going to learn about single cycle data path. Basically, there are three different types of instructions. One, memory reference instruction. Second, arithmetic logical instruction. Third, branch instructions. In these three different type of instructions, we use ALU for various purposes. In the memory reference instructions, we use ALU for address calculation. In arithmetic logical instructions, we use it for operation performance or to execute an operation. In the third one, the branch instructions, we use it for comparisons. After using ALU for the respective operations in three different instructions, what action is being performed? In the memory reference instructions, memory is accessed either to perform read operation or write operation. Read operation will be performed in the case of load instruction and write operation will be performed in the case of store instruction. And in the case of arithmetic logical or load instruction, the ALU, after performing or using ALU, the data which is the output of ALU will be returned into the memory or into a register. In the case of branch instruction, we are supposed to get the next instruction address. The next instruction address could be based on the comparison and also it could be based on the program counter value, that is PC value. So there are two possibilities in this case, that is the change the next instruction address based on the comparison or otherwise change the next instruction address by incrementing the PC by 4. First of all, we will see the data path design step by step, and in such a case we are going to see what are the units we require in order to perform the fetch instruction and incrementing the program counter value. So the elements what we require are memory unit, program counter, that is PC we are representing here, and an adder to increment PC. So the first one, in this case, we are going to use different memories for instructions and data. So in the case of fetching instruction, we require only instruction memory. So in the instruction memory, the input will be the instruction address. The address will be provided here and the instruction from this memory will be fetched and it is the output of this instruction memory. In the case of program counter, we are going to give the address into the PC which is holding the next instruction address. Output is again address which will be given to the memory from which the instruction is going to be fetched. So this PC output will be the input of your instruction memory. The adder will be having the inputs on which we are going to perform the addition. Sum is the output of the adder. So these three units, that is instruction memory, program counter and adder, are used and combined in order to design a data path for fetching instructions. So here if you see, as I already specified before, the output of the PC is becoming the input of instruction memory. We are going to fetch the instruction from the instruction memory which is the output of it. Now in order to increment the program counter, the present address of the PC is given as one of the input to the adder and the another input of adder is 4. So as we have specified already, the program counter will be incremented by 4 in order to get the next instruction address which is being done by this adder. So the output of the adder will be connected as an input to the PC. So once we are giving this address from the PC to the instruction and fetching is completed, the PC will be incremented by 4 and again updated in order to point out to the next instruction to be fetched. So this is the data path which is used to fetch the instructions and also to increment the program counter value. Next, we are going to see what are the units we are required in order to perform arithmetic and logical operations. So here there are two elements what we require in order to perform ALU operations, that are register files and ALU. So here in the case of register files, you can see that read register 1, read register 2, write register, write data are there as inputs and read data 1, read data 2 are outputs. So here it is like register write, which is like a control signal what we are supposed to specify in order to write any register of these registers. So read register 1 and read register 2. If we are enabling these two, then we are going to get the data from these two registers as output of read data 1 and read data 2. And suppose if we want to write into a particular register, then the write register will be enabled and the data what we are going to write into the register will be given here, and the register write will be enabled here. So into the selected register this data will be written. This 5 indicates that there are 32 registers in this register file. So this data 1 and data 2, which is read from different registers, will be given as input to the ALU in order to perform the operation. So here this 4 indicates that 16 operations can be performed using this ALU. So whatever the operation we want to perform, that corresponding control signal should be given in this case of ALU operation. That is addition or subtraction, whatever it is, 4 bits need to be provided. So ALU result will be the result of the operation what we are giving on the input as the input to the ALU. This 0 signal will be used in the case of branch instructions, which we will see later. Next, in the case of memory instructions, in addition to the register file and the ALU, we need 2 more elements, what we say as data memory unit and the sign extension unit. In the case of data memory unit, the address from where the data is supposed to be fetched is the input, and write data also will be there as an input in order to perform a write operation, that is into particular address. If we want to write a data, address will be given and write data will be given. Whatever the data we are going to write into the particular address will be specified here. If we are performing memory write operation, this will be enabled. If we are performing memory read operation, this will be enabled. So if we are performing memory read operation, read data output will be coming, and if we are performing memory write operation, no output will be there from the data memory. 16-bit sign extension is there, that is this will be used in order to extend 16 bits into 32 bits. Whenever we are giving an offset value, 16-bit offset value only will be given, but the data size of this processor is considered as 32, so 16-bit will be extended to 32 using sign extension unit. Next, the branch instruction. Till now we have seen 2 different types of instructions, that is load store and also arithmetic and logical instructions. So the last one is nothing but branch instruction. In this case we are going to see about the branch if equal instruction, which will actually have 3 operands, out of which 2 are registers and third one is the offset. So here we are supposed to compute the branch target address. So here we are going to verify whether T1 and T2, in this example T1 and T2 are equal or not, and then branch target address is calculated and branching will be taking place. So branch target address is calculated as sign extended offset plus PC. So this offset will be sign extended to 32 bits and will be added to the program counter content. And this branch target address will be updated to the PC if these two T1 and T2 are equal. If these two are not equal, PC will be updated by incrementing just with 4. So here in detail we have given the data path for branch instructions. So the ALU is used to evaluate the branch condition. So that is nothing but for comparison purpose we are supposed to use the ALU. So as we have seen before itself, 0 is there, which indicates whether both the inputs of ALU are equal or not. A separate adder is required in order to compute the branch target address. So here if you see, T1 will be coming from this, T2 will be coming from this to the ALU. Both will be compared in the ALU. 0 will be enabled, or we can say that 0 will become, output will become 1 in order to show that these two are equal. 0 will be disabled if these two are not equal. So whatever it is, the branch target address will be calculated. Only we can decide whether branch target address is updated with PC or not based on this branch control logic output. So here the offset from the instruction will be given as an input to the sign extension circuit or unit, and from 16-bit it will become 32-bit, and we are going to shift it left towards 2 times. Why we are shifting left 2 bits is nothing but increase the effective range of the offset by a factor of 4. Now we are going to see the combination for the data path for the memory instructions and the arithmetic and logical instructions. So the elements whatever we have identified in order to design the memory instructions and also the arithmetic and logical instructions we are combining. We have seen that there are some common elements in order to perform memory instructions and arithmetic and logical instructions. So here the register files will be having only one data output, or we can say the ALU will be used in order to perform the operand address. In the case of memory instructions, the result of ALU will be the operation output in the case of arithmetic and logical instructions. So here what happens is, in the case of memory instruction, the read data 1 only will be provided to the ALU. The output of the multiplexer will not be considered from the read data 2. It will be considered from the instruction only. That is, in order to calculate the operand address, the ALU will be used in the case of memory reference instructions. So the operand address will be given to the data memory as its input, and once the address is provided, the data will be taken from the corresponding address, and the read data will be provided as an input to this multiplexer. So here memory read will be enabled, and memory to register also will be enabled. This ALU operation will be used in order to compute the operand address. This ALU source will be used in order to provide what source as a second input to the ALU, whether it should be a read data 2 or it should be a sign extended form of which is taken from the instruction. So in the case of memory instructions, it will be the sign extended data as an input to the multiplexer, which is the output of the multiplexer and input to the ALU, and read data 1 will be the second input, which will be used to calculate the operand address, and the corresponding data from that address will be taken to the input multiplexer. So from the multiplexer we are going to store it into one of the registers. Suppose if we are performing the arithmetic and logical instructions, then read register 1, read register 2 will be the inputs from the instruction it will be taking, and read data 1, read data 2 will be the inputs of your multiplexer. That is, ALU SRC will be using to select read data 2 as the input of ALU here, and read data 1 will be obviously the second input, and corresponding operation will be selected here, and ALU result will be the data now but not the address. So please remember that ALU result will be the address in the case of memory instructions, ALU result will be the data in the case of arithmetic and logical instructions. So here, instead of giving this ALU result to the address here directly to the input of the data memory, it will be directly given as input to the multiplexer here. So the memory to register will be selecting the 0th input of the multiplexer, which will be in turn giving to the write data. So the output of the operation of ALU will be writing into particular register here in the case of arithmetic and logical instructions. So because we are not showing that here the ALU result is given either to data memory or to the multiplexer. Here if we are disabling both memory write and memory read, obviously the data memory will not be considered this ALU result as its input. So what happens, the next stage is nothing but ALU will behave as the input to this multiplexer only, because the data read is not there. If it is there also, the memory to register will be helping us to select the 0th input of multiplexer as the output of the multiplexer. This is the data path design for memory instructions and arithmetic and logical instructions. So fetching and incrementing PC data path is combined with memory instructions and arithmetic and logical instructions. If you see this particular part, that is register, sign extension, this multiplexer, ALU, data memory multiplexers, and this is all there in the case of previous diagram. So here if we can see that this is all there, and in this data path we are using branch instruction is included, which we have already designed for branch instruction. This part is used for branch instruction to be calculated, and this is part which we have seen in the case of fetching an instruction and also the incrementing the PC. That is, if you can see here, instruction memory is coming new, PC, adder, shift left 2, adder again, multiplexer here. So this is a complete data path we can say for fetching an instruction to perform an operation, that is if whether the instruction is memory instruction or arithmetic and logical instruction or branch instruction. So if it is a arithmetic and logical instruction, how is it going to be? Then first of all, we all know that PC will be having the instruction to be fetched, that is the address of the instruction to be fetched, which is given to read address. So from instruction memory, instruction will be taken. So let us say that we are performing arithmetic logical instruction. So from where, and we are performing addition instruction. So read register 1, read register 2 will be giving the registers from which we are going to read the data, and read data 1 and read data 2 will be giving the registers output actually. So here ALU SRC will be selecting the read data 2 as an input to the ALU, and this ALU operation will be selecting the addition operation. So this ALU output will become addition of read register 1 and read register 2. So this will be given directly into this multiplexer input. Memory register write, memory write and memory read will be disabled in this case. So memory to register will be selecting this input of the multiplexer as its output. So here we are going to make this to be return data, and from the instruction into which register we are going to write will be selected, and this write data will be the output of the multiplexer. Register write will be enabled and it will be written into the corresponding register. This is how your ALU operation, that is arithmetic and logical operation, will be performed. In the case of memory instructions, once the instruction is fetched from the memory, we will be having read register 1 and it will be output from the read data 1 to the input of ALU. Here we are using ALU in order to calculate the operand address. So offset will be provided in the instruction, which is sign extended 32 bits, and will be provided as input of the multiplexer, which is the output of multiplexer to the as an input to the ALU. So ALU result will be the operand address, so which will be the input to the data memory. Read data will be the operand value, which is given to the multiplexer. So this is how your memory instructions will be working out. In the case of branch instructions, ALU will be used for comparisons. So again here, after fetching the instruction from the memory, read register 1, read register 2 will be taken, and read data 1 will be the input of ALU, and second input will be read data 2. So both will be compared. If both are equal to 0, then the 0 will be enabled, otherwise it will be disabled. So here the offset which is used to calculate the branch target address will be sign extended and also shifted left 2 bits and provided as an input to the adder. Already we have incremented the PC by 4, which is going to be pointed to the next instruction address, which behaves as an input to the second adder here. So now the ALU result here, that is the adder result here, is nothing but PC plus this shift left 2 operation, that is this is branch target address. So this multiplexer is used to select either this PC address, this updated PC value, or branch target address. So if branch is taken, which depends on the 0, if 0 is enabled, branch will be taken. If 0 is disabled, this branch will not be taken. So this input of the multiplexer will be considered. So this 0 will be given as a selection line for your multiplexer, and hence the PC will be updated with the output value of the multiplexer like this. So this is a simple data path. If you see here, now we are having the different control lines, that is register write, ALU SRC, ALU operation, memory write, memory read, memory to register, or PC SRC. All these are nothing but control signals. So these control signals are going to combine into a single unit, and in fact in this case we are going to generate the control signal unit with the two levels. We'll see the control signal units after discussing the instruction formats. So in the case of MIPS instruction format, for the R-type instruction, we are supposed to see that the bits 26 to 31 is 0. So this bit 0 indicates that it is a R-type instruction. R-type instruction is nothing but arithmetic and logical operations to be performed. And 26 to 31, if it is 35 or 43, it indicates load or store instruction. 35 is for load, 43 is for store instruction. 26 to 31, if it is 4 value, then it is branch instruction. If it is 0 0 0 0 1 0 value, then it is for jump instruction. So these formats bits, whatever the classification is given, will be used in the case of designing the data path. Now in this figure we have provided the control lines also. If you see here, instruction 32 bits we have given as 0 to 31, and if you remember in the instruction format what we have specified before, 21 to 25 will be providing the first source value, 16 to 20 will be providing the second source value, 11 to 15 will be again in the second source value of another instruction type, 0 to 15 is the offset value, and 0 to 5 will be the ALU control function values. So I'll just go back and show those again. So if you see in the arithmetic and logical instruction, 21 to 25 is the first source, 16 to 20 is second source, 11 to 15 is the destination operand value, and 0 to 5 is function operation value, which is the control signals for ALU. Now you can see here ALU control will be having 0 to 5, 21 to 25 is first read register, 16 to 20 is second read register, and 11 to 15 will become the destination register in the case of ALU operations or R-type instructions. Now if you come to the load or store instruction, 21 to 25 will become the source operand value, 16 to 20 will become the destination value, 0 to 15 will become the offset value. So here 16 to 20 will be given as a input of another multiplexer, which need to become as a write register, that is destination register in the case of memory instructions. 0 to 15 is given as sign extension input. Now coming to branch instruction, again 21 to 25 is one source operand value, 16 to 20 is another source operand value, 0 to 15 is offset value. So here in this case 21 to 25 will be read register 1, 16 to 20 will become read register 2, and 0 to 15 will become offset value. Okay, now let us, this is like one stage of control signals which is going to be generated to the ALU. Now if you see this diagram, register write, ALU SRC, ALU operation, register destination, all these are control signals which are combined into single unit and specified as control unit in this case. So this control unit will be having the input as 26 to 31 bits, which is taken from the instruction. This 26 to 31 bits is nothing but which indicates what type of instruction and what type of operation it is going to perform. So first of all, whether it is arithmetic or logical instruction depends upon these 26 to 31 bits, which is 0. And after determining whether it is arithmetic or logical instruction, then actual function will be determined using this 0 to 5 bits. This is nothing but two-stage control signal generation or two-stage control unit design. So here, once it is deciding whatever the operation type it is, it will generate different types of control signals and which will be given as inputs to the corresponding units actually. And here the next 3 slides will show you the example for different kinds of operation. That is, the control signals are enabled, and also the units what are enabled. The units are enabled which is helpful in order to perform the corresponding operation only. That is, in order to perform add T1, T2, T3. We are performing T1 and T2 addition and storing in the result to T3. So in order to perform this operation, whatever the units and whatever the control signals are needed, that only are used in this, or that only are highlighted in this diagram. If you see, PC will be giving the input to the instruction memory. 21 to 25 provides T1 value, that is read register 1. 16 to 20 will provide the T2 value, that is read register 2. So here 11 to 15 will give you the T3 address. So you can see that this is disabled. Okay. Now the input of the multiplexer, only one is enabled, and this selection line of the multiplexer will be register destination will be selecting the 11, whatever the address is given in the 11 to 15 bits. That is T3 will be selected in the case of write register. Out of 0 to 15 bits, 11 to 15 are already given here, and the rest of the from this 0 to 15, 0 to 5 bits are given to the ALU control, which actually shows that it is add operation to be performed. You can also see that this particular part is disabled, and this multiplexer is getting only the input from read data 2. So ALU inputs are read data 1 and read data 2, and this ALU control signal is generating add control signal to perform its operation. So because it is performing the arithmetic and logical operation, or we can say add operation, data memory will be disabled. So the ALU result will be given directly as an input to this multiplexer, and this multiplexer will be getting the control signal memory to register from the control unit, and the output of the multiplexer will be given as write data to the write data. Already write register is selected. By giving the register write signal, this data will be written into the T3, which is selected as write register. This completes the operation of your addition. So meanwhile, the PC will be updated with the addition of 4 bytes. So here this will be disabled because this is not a branch instruction. Next, data path for the load instruction. Again, this part will be disabled because it is not a branch instruction. PC, we will say the address will be provided to instruction memory, instruction will be fetched, and because we are performing load instruction, the 21 to 25 will be the first operand value, that is into the read register 1. The second operand value will be the offset value in order to calculate the data from where we are supposed to take it. So 16 to 20 bits will be given to the inputs of the multiplexer instead of to read register 2. So here we are going to select the write register, into which we are going to store the value. So, and 16 offset value will be given to the sign extension bit. 16 bits will be sign extended to 32 bits, and this 32 bits will be the input of the multiplexer. As we don't have the read register 2, obviously read data 2 will be disabled. So this whatever is read from the register 1 will be the input of the ALU. So this offset value will be added to the read data 1 to get the address of the operand. So this address of the operand will be provided to the data memory. So this data memory will be giving the data from the corresponding operand address, and it will be given as an input to the multiplexer, and this multiplexer will be giving this to the write data. We already have taken the write register, so we are writing this data into this particular register by using register write control signal. And at the same time, PC will be updated PC plus 4 only, because it is not a branch instruction. And the last one is branch on equal statement. Now you can see that branch on equal statement we are executing. So branch data path is enabled. First instruction will be fetched, and then read register 1 will be there, read register 2 will be there. So here these two register values are going to be compared in the ALU. So read data 1, read data 2 will be the inputs of the ALU. They are compared, and this 0 will be disabled or enabled based on the data in the read register 1 and 2. So let us say that 0 is enabled, that is 0, both are equal actually. So this will be the input to the branch instruction, and at the same time, on determining that this is a branch instruction, this branch instruction will be enabled. So if both are equal to 1, the multiplexer will be given the selection line as 1. So the branch target address, which is calculated using this adder, will be the output of the multiplexer, so which will be updated to the PC and branch will be taken. Suppose even though this is a branch instruction, this branch will be enabled, but if this is not equal, that is condition is not met, 0 will become disabled, so output of AND gate will become 0. So what happens? The branch target address will be calculated, but branching will not be taken place because the resistor 1 and resistor 2 are not equal. So the PC will be updated with the PC plus 4 only. That is the case of data path for branch on equal instruction. This table will help you to know what will be the control signal values for different kinds of operation. The references what we have followed in order to discuss this single cycle data path is David A. Hennessy Patterson, Computer Organization and Design, the Hardware Software Interface, 5th edition. Thank you.